We'll complete the square on this quadratic to find that the vertex is at x equals 3/2. So on the range that we're interested in, from x equals 5 to 15, we have that p of x is increasing. We'll check the values of p of x on these endpoints. Plugging in 5, we get that p of 5 is 1, and p at 15 is 171. On the left-hand side of our given equation, the floor of the square root of p of x, the floor function always returns an integer, so this expression is an integer. This means our right-hand side is also an integer, which means underneath the square root sign, p of the floor of x is a perfect square. So let's list out the perfect squares in this interval. Here they are. We'll let n be the floor of x. So when we plug it into p, our solutions in n must be integers. We'll start by letting p of n be equal to our first perfect square, 1, and we'll substitute, collect all the terms, and factor to try to find an integer solution in n. Here n, which again is the floor of x, is 5, which is in our interval, which means x itself is greater than or equal to 5 and less than 6. Let's try our next perfect square. We'll set p of n equal to 4 and substitute, collect all the terms, but we see here there are no integer solutions for n, which is the floor of x. So we'll go on to the next perfect square, which is 9. We'll go ahead and subtract 9 to collect all the terms and factor. And here's our next integer solution for the floor of x, which is 6. This means that x is greater than or equal to 6 and less than 7. We'll keep going with 16. Subtracting 16 from both sides of our polynomial gives us no integer solution, so we'll discard and try p of n equals 25. This quadratic has a constant of -34, no integer solutions. 36 is our next perfect square, no solutions here. We'll try 49 and 64 and 81 and 100. Just a few more left. We'll continue with 121. I think this will work. Here, our solution in this interval for the floor of x is 13, which means x is greater than or equal to 13 and less than 14. 2 more perfect squares, and no more integer solutions. So we'll call these cases 1, 2, and 3, and try to find our bounds on x. We'll start with case 1. This has x between 5 and 6, gives us that p of the floor of x is equal to 1. This is the same as the square root of this is also 1, and this is the same as the floor of the square root of p of x. Inside the floor function, this means that the square root of p of x is going to be between 1 and 2. We'll square this through, and p of x is between 1 and 4. We'll substitute for this polynomial, add 9, and complete the square. In the middle, we have the square of x minus 3/2, bounded by 49 over 4 and 61 over 4. And we'll take the square root. We need x to be greater than 5, so we're just looking at the positive square root and adding 3/2. I want to check to make sure this fraction is less than 6. We have root 61 is between 7 and 8, so adding 3 and dividing by 2 makes this less than 5.5. So we're still within the interval of our case 1. So our overlap, which makes the equation true, is x between 5 and then the upper bound here, 3 plus root 61 over 2. And we'll repeat this for cases 2 and 3. Case 2 has x between 6 and 7. On this interval, p of the floor is equal to 9. So the square root of p of the floor is equal to 3, which means the floor of the square root of p is also equal to 3. Inside the floor function, this is between 3 and 4, and we'll square all 3 sides. So p of x is between 9 and 16. Again, we'll replace this with the variables and complete the square, and then we'll take the square root. Double checking, root 109 is between 10 and 11. Adding 3 and dividing by 2, we see that this is in our interval. So for our second case, to satisfy both of these, x is going to be between 6 and 3 plus root 109 over 2. Let's return to case 3. That was x between 13 and 14. And p of x is 121 on that interval. So the floor of the square root of p of x is 11. Removing the floor function, the square root of p of x is between 11 and 12, and we'll square. So p of x is between 121 and 144. Substitute and add 9 and complete the square. And take the square root and solve for x. And checking root 621, that's between 25 and 24. So this expression is less than 14. So our solution on this interval is between 13 and 3 plus root 621 over 2. Now let's find our probability. The denominator of our probability is the range of our interval from x equals 5 to 15, and the numerator is the range of these three intervals, so we'll subtract to find the length of that range. For case 1, we're going to take 3 plus root 61 over 2 and subtract 5. For case 2, subtracting the upper bound from the lower bound, and the same thing for case 3. Now let's try to simplify. This is 1 over 10, and we'll tackle these fractions. We have 9 and these square roots, all multiplied by a half, and then our integers add up to minus 24. Let's factor out the 1/2. So this becomes minus 48, and combining these terms, we have minus 39 all over 20. The problem asks for the sum of these terms. Careful to get this sign right, and this adds up to 850. If you'd like me to solve any other math contest problems, please leave them in the comments.